17th. Yeah, there probably will be people still joining in, but we will start up a little bit about the information about today's webinar talk, the STARS talk that we hold in the Alliance of STARS EU. And this talk will be the 17th in the row of our talks. And like normally, it's up to 1 hour where the presenter have their time, 30 to 40 minutes of introducing the subject, giving the information, the knowledge on the topic chosen. And afterwards, we will have the opportunity to have a dialogue, ask questions, and talk with Professor Benjamín González Diaz, who is the speaker today. So yeah, we are in a couple of minutes into the meeting, but I think that we actually are going to start it up. But before we do that, I will like to inform all that this meeting will be recorded and be able to share through the channels of the STARS EU. So by still be a part of the meeting, you agree to that. If you don't agree to being part of the meeting and that your face and name could be viewed, then you need to leave now. Otherwise, that you agree upon that you're part of this recording and this webinar. Today's topic, a very important topic, not least in the presence and in the view of the energy transition that the world is going through. We are very much electric. All the facilities, all the gadgets, everything is dependent on electricity. And we have a large challenge for the future, how the electricity is going to last. We are changing energy systems. We are working on different forms. So today's talk by Professor Benjamín González Diaz on energy transition applied in isolated systems, current and future challenges, is therefore much really important and really interesting. And I'm truly looking forward for having hearing about this and be able to learn more about this important subject. So by this, I will. I do not intend to introduce Professor Benjamín González Diaz more. If you are very well known within the Alliance, but please, if you want to introduce yourself, please start with that. And the floor is yours, Professor, and we are most eager and interested to hear about your reflections and knowledge about today's topic. So please, Benjamín.
So thank you very much, Professor Peterson. So and also I would like to thank you your introduction and also your effort with the STARS EU talks, and also to the team that has been behind you preparing this talk. So I will try to share my presentation. I think it's this one. Okay. I hope you can see it. Okay, can you see it, my screen?
Yeah. We see it perfectly. Fine.
Okay, perfect. So before to start to talk, I want to say that I scheduled this overview. It's not exactly a presentation. It's an overview about the challenge that we will have in our grid, more or less in these issues. So about me, I have a bachelor in physics from University of La Laguna in Tenerife, in Spain. I carry out a PhD studies also in physics with the application of borosilicon nanostructure in silicon-based solar cells. So from the very beginning, I've been involved in the renewables market, using the technology to create new things. I had the opportunity during my PhD to collaborate with the ISA Fraunhofer in Germany in the period that I was there. And finally, I come back to my island and I start to be a researcher at the Technological and Renewable Energy Institute located in the south of Tenerife here in Spain. After the presentation of the PhD, I moved my skills from the creation of solar cells to the creation of solar modules and several components inside of the renewable energy. And also, I've been working in the wind power technology. I had the chance to apply for a position at the University of La Laguna, my former university, in the area of electrical engineering in 2011. I'm still here working in the same area. And also, I joined to the Starseed Alliance when my university started in 2022. So actually, I've been moving from the development of new materials and electronic electric components inside of renewable energies to energy planning, energy policy, and also how to apply several measures in the building energy management. There is a QR code there if you're interested to see my courses and the publication that I've been doing during these years. I also belong to the electrical engineering and bioengineering group at ULL, and there are 3 subgroups over there. One of these one is devoted to the brain connectivity and health and diseases that is led by the Professor Ernesto Pereda, also an active member of the Alliance. The other part is devoted to neurological modeling and responses, and I belong to the third part, the renewable energy systems, to create new components, devices, and energy planification. So it's necessary to think about the net zero carbon emission, or what's the meaning of net zero carbon emission that we have been thinking during this time. So in order to prevent the worst impact of the climate change, perhaps the carbon emission must be stopped, not only be reduced, must be stopped during an perhaps not too much time. Net zero emission sometimes is also called carbon neutrality. It's the achievement of balance between the carbon output and the carbon reduction of a given identity, for example, on a city, an island, or a country. Net zero emissions cannot be achieved without the process of decarbonization. So what's the meaning of decarbonization? In that case, it's the process of phasing out fossil fuels to be used inside of a building, transportation, energy systems, and so on. At the community level, this issue must include everything from generating with renewable energy to promote electrification of building, vehicles, and also to create bicycle and pedestrian-friendly streets that could reduce resident needs to use gas or fuel-powered transportation. If we consider the decarbonization process, perhaps we can divide in 4 parts. In the case of the European directive, more or less all the packets are devoted to these 4 issues or big issues, to be precise. In that case, regarding to the electrified and accessible transit is a need to provide the community with low-cost, convenient, and safe low or no carbon transportation options. Among the possibilities that has been considered around the world about the carbonization side of transport is to enhance the use of bicycle or also to enhance the pedestrian infrastructure. Also to use another kind of fuel without pollution produced by its use by any compound, or also to electrify the public transportation. Also, there are several ideas to make an electrification of the municipal or commercial fleets, and there are several rules, intensity, uh, economic issues to force to the people to move to an alternative fuels. Also necessary to develop in the case that the electric vehicle will be used to enhance the infrastructure around the cities, around the countries. In that case, it's a little bit more complicated, the heavy-duty transport and also the flight and ship communication. Therefore, another alternative as the use of H2 has been considered. In case of the building, there are two main things. One of this one is regarding to the use of new directive and new benchmarking policies in order to avoid the fossil gas infrastructure inside of the new building. But in the other way, we need to take into account that in Europe, approximately the 43% of the primary energy is devoted to the buildings. So in that case, there are several economic lines devoted to promote the change inside of the building, to reinforce the infrastructure of the building, to avoid the use of the heating, or to move from the current technology to another greener technology. In this sense, also from the European Commission, there are new codes that has been analyzed in order to establish the rules for the buildings in the future. Finally, renewables seems to be one of the most promising ways to carry out the decarbonization in order to make a project where, in that case, the role of the people will be more important in the production lines. I mean, European community has been pursuing the idea of the energy community, where the association of several prosumers, so producers and consumers, can be put together to offer services inside of the system. In that case, it's necessary to allow the integration of renewable energy inside of the system by means of power purchase agreement, battery storage, and enhanced grid connectivity, and also to make grid interactive efficient buildings. So taking into account that this is the main idea, we need to have a look how is currently our grid in order to understand how this transition will be done. Until yesterday, all the system, electrical system, has been prepared to start with the generation, normally in several points around the country, an island, a place, and so on. And using the transmission lines, we can transport this energy from the generation station, the central stations, to the final distribution, so to the final customers. In that case, the power flow is coming from the generation to the distribution, and all the infrastructure is ready to be used in this sense. So it means that all the devices that we have inside of the system are ready to carry out the energy transportation in this sense. In the case of that picture, from the left to the right. If we consider like that, the scale of capacity, well, I took that as transparency and put all systems, but this is not all. This is still over there. We are making the transition of this kind of system where the generation and also the storage in the order of gigawatts per megawatt and a higher power. There are several lines to connect to the transmission network in high voltage. And depending on the final customer, heavy industry or very big consumers, they receive directly in the transportation lines the energy. However, we can make a transformation of the energy using several transformers to carry out to different voltage level to the final customers that we have in Europe an average of 230 volts in the case of the residential. In the case of industry, it's around 400 volts. And if we have a very big industry, we will have over 1 kilowatt the chemistry of the energy. Nowadays, the grid is a little bit more complicated. So we still have the same things that are generating the energy, like nuclear, hydro, and the fossil fuels. In that case, they keep exactly in the same range between the gigawatts and megawatts. But we are introducing new system. When we have a distributed system, in the case of onshore wind or offshore winds, and also utility scale solar facilities, we will have also in the same range than gigawatts and megawatts stations. However, we can see there that we will introduce the household solar and storage. So we have now anything that was the previous slide at the end of the system now is part of the generation. We are using exactly the same grid. Remember that the grid was planned to be used from the generation to the final customer. But now we can see that the final customer is also a producer. This is the well-known prosumer. Therefore, we have right now bidirectional power flows. This is a constraint because the lines were not designed to do these things, and several problems will arise if we are using the system like that. In the case of the demand, we are increasing our capacity to make an interconnection with different lands, with different countries, territories, and so on. We still have the heavy industry, light industry, but also we introduce another element, that's the transport. If we are using the electrical vehicles to be inside of the system, we need to take into account like a load. But also, we have the possibility to use several vehicles, like vehicles to the grid. What does it mean? So this vehicle can receive the energy, storage in their batteries, but if it's required, they can use the energy storage in their batteries inside again to the grid. Therefore, this is also a bidirectional power flow system. At the very beginning, in the first one, the first slide, it was more or less clear how to make the frequency balance. So in Europe, we have 50 Hertz. In States, we have 60 Hertz, and depending on the part of the world, several systems are with different frequencies. The election of the frequency normally is the answer to consider if they want to use more for the industry, for motors and so on, but it's an historically decision. So there is not any technical advantage to use one frequency and another one. The only thing that at the very beginning, the frequency of the system was around 20 Hertz. So it means 20 times per second, or 25, but they decide to increase because it's more or less the frequency that we are blinking with our eyes. Perhaps several stroboscopic issues appear. Therefore, they decide to move to the other frequency. So, but this discussion is exactly the same independently of the frequency that we have. In the case that we have a well-balanced system, we have the generators. Think in the conventional generators, they are rotating. So this is a mass that is rotating to generate the energy. And the consumers are in the other part, okay? And if everything is right, we can keep this frequency exactly in the, well, we have a small slip, a small variation, but we can keep exactly in the range that we need. In the case that we have more generation, for example, we decide to go out right now and switch off the lights of our houses, we reduce the demand that we will have, and the generators need a little bit time to react to this decrement of demand. In that case, the frequency move a little bit under the desired frequency. In other way around, in the case that we increase our consumption, the generators need to accelerate a little bit to adjust these things. It produces that the frequency will increase a little bit more. So therefore, we are not consuming constantly the energy. So it means that we need to adjust. I want to say hour by hour, but honestly, it means that it's not true, that it's second by second to establish everything there. This is a typical graph of a typical consumption pattern that we have in every part. We can see, well, during the night, we have a base consumption. Normally, this is devoted to if we are thinking in services or several companies that they are open during the night, or this pattern, but without the units, could be considered, for example, a typical pattern that we have in a house. During the night, perhaps we are recharging our mobiles or any other device, and also we have the fridge and any other device in standby. At the beginning of the morning, we rise the consumption because we have a shower, we took coffee, we start to work with our computers and so on. We are producing, and when we are coming back to our houses, we are preparing the dinner, preparing the things for the next day, and so on. And we will increase again these things. But of course, it depends on the season that we have, it depends on the day. So several techniques must be performed in order to analyze how is the pattern. In that case, this variability is not a technical issue. This is a social issue, how the people is using the energy. And it's necessary to modulate how it's going on in order to be ready the next day to produce the energy. So when I was preparing this slide, I took a snapshot of the demand of my island. Here you can see the graph. You have the red graph, the red line. This is a squared one. And this is the order to the different devices that are producing the energy inside of the system to be active or not. In the case, it's not possible to see because it's so close to the yellow one. The planet one is the green one, and the real one is the yellow one. We can see how the demand is going on over there. In the bottom, we can see the complete renewable energy production that we had in my island in Tenerife. Well, this was expected. We can assume that PV production is on a normal distribution, but due to the clouds, maintenance, and operation, and so on, we can see in the right button how the production is absolutely with a lot of intermittencies. So one of the main problems to put renewable energies inside of the system starts with the intermittence that we have with these things. When we have a thermal machine, except when we have an operation and maintenance, we will have all the year working these things. But for example, in the case of the photovoltaic power plant, in the case of Tenerife, the average production hours per year is between in the range 1,500 to 700 more or less. It represents less than the 20% of the time. Therefore, when we are talking about renewable energies, to make an old transition, it's necessary to have any technology of power storage, batteries, hydropower, or any other that are available inside of the systems. To do these things, it's quite important to invest in the infrastructure. Changing a cable is not like to change in a house. So these projects demand a lot of effort, not only economical effort, so a coordination to avoid any blackout, to avoid any contingency inside of the system, to put in parallel, to put in service, and also to try to make this infrastructure very efficient to replace the old one. Also, it has a cost, and depending on the land, the country, island, municipality, and so on, this cost could be a little bit higher. And also, they can last several years, even more than a time frame that we can consider the profit of the project. Also, it's very important to take these issues into account to create an adequate policy and a strategy to carry out this transition. So the lack of infrastructure is also a very huge problem that we have, because wind and solar energy can be better investment when lifespan costs are considered. Nowadays, the lack of infrastructure, remember that infrastructure was planned, was thought from the generation system to the final customer. So this infrastructure, this lack of new infrastructure is a huge barrier to the renewable energy development. Here, in an isolated system, we have a penetration normally no more than the 20%. And this is mainly due not for the ability to install things or the power that we have inside of the system. It's how to manage the power inside of the rules to keep the system alive, to avoid a blackout. Because due to the intermittencies that we have with the renewable energy, it's quite complicated to manage more than the 20%. In this sense, here we have a production, typical production that we have with wind power. This is green. And we have the load, the desired load that we have. This is in yellow. This is the demand, the final demand that we have for the final customer, and the net load. So this energy is coming from another thing except from renewable energy. So we can see here to manage hourly, we can see that is a little bit less than 1 week. When we have the resource of wind, for example, on 19th of February, it's very nice. We are increasing, but the other part, the net load, the other system must react to adapt to the load that we have. So they must be ready to increase and decrease the power to accomplish the demand of the final customers. So it means that several equipment must be ready to entry and to slip the power that they have to accomplish the demand. But in the case that we don't have any resource, in the case of PV during the night, it's more or less clear. But for example, if we have wind and we have a drop that is not expected, we need to increase quickly, because if not, we can reduce a partially blackout or a total blackout of the system. In the following graph, we have several issues regarding the renewable energy challenge. We have, let me put here, this one. Here we have, for example, a typical graph of the energy excess in one sunny day, okay? We have the demand here, and we have the PV production, okay? In this PV production, we have this surplus of the energy. There are several things that we can do with this. If we can not move this energy to another part, like this one, because we have an infrastructure to accumulate the energy, we need to make an curtailment of the energy. And this is also and a challenge from the state to the private investors, because when anybody wants to put one of these installations, it's making several calculus about the profitability of the installation. If there are too much PV power inside of the system, the system operator send an accurtainment signal to stop the production of renewable energy. Therefore, it's necessary in that case to invest in any kind of storage system inside of the system. Also, there are another kind of issues that we need to have into account. Here we have an photovoltaic production, okay? Well, ideally, it must be like a normal function, but here we have a very huge oscillation. These oscillations are very typical in a cloudy day, okay? In that case, the other system must react to avoid any problem to the final customer because the power drop a lot of time. And also here we have, for example, a very cloudy system, and we have a 100 rated power fluctuation. But this is very sharp, this is very short. So it means that we need to, if we do not have any accumulation system to give very quick this power, we have the challenge to use the other devices that we have inside of the system to put as soon as possible the energy, and when the renewable will start again there, to change all the system to decrease the power of this thermal unit. But remember that the thermal unit is rotating, it's not immediately, so it needs time. Therefore, several fluctuations of the frequency will happen over there, and the system is ready to be protected with under frequencies and under frequencies, upper frequencies and under frequencies. And therefore, to manage these things is a little bit complicated. Here we can see the same installation. This is on a clear day. This is the profile that we have, but this is on a cloudy day, how it's going on. So around 20 years ago in California, there was a huge promotion of the residential photovoltaic installation on the roof of the buildings. Well, the system must accomplish the total demand that we have. But due to this installation, people perhaps do not need the energy at the midday. Therefore, the system must reduce the energy provided by the system operator and the other producers, conventional producers. What happened? That we reduce this minimal, technical minimal that we have here, we can enter in an instability system that can collapse the system because we have not enough inertia and enough spinning reserve to accomplish the demand and all the issues that we have. Therefore, in several countries, several lands, they are receiving a signal of curtailment because they are introducing too much PV power inside of the system, and it's not possible to manage this one in safety condition of the grid. Well, in the case of renewable energy, in particular in that picture, is an photovoltaic power, they are not a rotating machine. They are using power electronics that actually they are using the frequency of the system to replicate this frequency and entry directly of this one. This system is called inverter. It's passing from DC power to AC power, and this is called grid following because any system must give the frequency in the system, and these devices are copying the frequency. So it means that I have this inverter here and I move to the United States, they can work properly because they are replicating exactly the same waveform at the same frequency where they are connected. But this introduced another problem. Remember that the lines were planned and installed thinking from the generation to the final customer. But now, one customer can have a PV power plant at the end of the line. What happens when we have at the end of the feeder and a large PV plant? So the voltage can increase over the limit that we have, producing a switch off of the PV power plant, or even a switch off of the transformer or the line. So therefore, it's necessary to make a regulation of the voltage inside of the system. There are so many ways to do that, but the problem is not from the technical point of view. The problem to regulate this one, for example, with reactive power, is there is not an law to do that. There is not a regulation to do that. Therefore, it's necessary to create a regulation in order to know how we can carry out this transition and how we can keep it safe inside of the system. Let me tell you a little bit about the energy market, how it's works, because I want to make a comparison with the rules of an isolated system. Currently, an energy market normally is on a country level. People is offering the capability of the different technologies. For example, we can enter with renewable energy and also nuclear with a price, and then we start to introduce another technologies. When we accomplish the demand, this is made hourly, and also there are three kinds of contract and a long-term contract. They can assure, for example, the entry of renewable energy and a daily market that is performed between 24 hours and 48 hours before. And also there is an intraday market to make an adjustment, small adjustment to several issues. So the final technology that is entry here is the technology that is giving the price to all the bill that we are paying, okay? And all the producers are receiving exactly the money of the last one, okay? And you can say, okay, but renewables are cheaper than gas. But well, the market rules is telling to you that they will receive exactly all the money from this point, okay? When you have this one, okay, and you have this power of renewable nuclear and the other things, you make a simulation of the stability of the grid. If the stability is okay, we can proceed with this market, okay? If not, it's necessary to make any adjustment and, in the worst case, to review again the energy market schedule, okay? So now we are moving to isolated system. It's important to know that in the case of Europe, there are about 300 islands that represent approximately the 6% of the territory, and 40 million of people are living approximately in the island. The Agenda 21, the island, are specific from both environment and development point of view. They are very fragile and vulnerable, and in the context of sustainable development, energy is the cornerstone of their planning strategies. So taking this one into account, they decide that non-renewable energy sources must be considered as provisional solutions and suitable as a long-term solution to the energy problem in Ireland. So they are pushing to carry out an energy transition. In this sense, it's necessary to compare how it's going on in the large interconnected grids, for example, in mainland, in all Europe, or in the case of smaller or isolated grids, and also, for example, in microgrids. In the case of larger interconnected grids, it's important to note that the economies of the scales can leverage economies in generation and transmission, leading to power per unit cost. Also, there is a greater stability because you have a system that is interconnected with another subsystems, and you have more than one way to connect the generation and the final customers. Therefore, you have a redundancy to enhance the stability across a larger area. Also, you have a cost-effective transmission. However, sometimes the larger interconnected grids can be very complex to manage, requiring a sophisticated control system and also coordination depending on the areas. Uh, Even when they are redundant, large grids can be still vulnerable to large-scale outage that can affect a wide area. In the case of the large grid, when you have a centralized power, often have a centralized generation and distribution system, which can limit the ability of local communities that are not so close to the generation to control their own energy sources. In the other part, we have isolated grids that can be a little bit more autonomy and resilience. We have certain flexibility because a microgrid can be tailored to specific needs on a community organization and can be used for a variety of energy sources and also to include storage methods. The transmission cost, because our transmission losses are less, so the transmission costs are lower in comparison with larger system. However, we have several disadvantages. We have a higher cost because to carry out the energy production, it has a higher cost because we have not a connection to import the energy. Also, we have an unlimited capacity because we have several limitations in our ability to support large load or complex industrial processes. So therefore, an isolated grid is limiting the economy of the zone because the introduction of bigger companies are very complicated. And also, the fragility of the isolated grid is mainly due to its small size and the lack of interconnection, making them absolutely vulnerable to disturbance. If we consider like this one, we can consider that perhaps it's more frequent to see in a blackout isolated system. And also that the systems in the case of European level are more stable, but it's well known that even in larger grids, we can experiment power outage, we can experiment blackout. These kind of things are not usual, but you have a very low frequency of probability of happening these things, but when they are present inside of the system, they can occur. And when anything happens, perhaps the system can collapse. Even when we are in large grids, you can imagine in small grids, because you have not the backup of another country, another land to provide you energy and to try to make a restart. The energy operation in isolated system is mainly based in 4 points, okay? The isolated grids, so you have not the possibility to include any other thing. You need to give the spinning reserve. I will explain this a little bit. Using the unit commitment, this is another way because we are not using on the market, and also it's necessary to have a backup inside of the system. Here we can see how is the provision of a production. Okay, here in black we have on a load, very stable load that we have here. Okay, this is very easy to manage. However, we need to have a look which equipment is necessary to provide the energy, and also we need to have another equipment ready to give the power if the main equipment fails. Okay, this is the unit commitment. It's called also the N-1 criterion. the other devices to produce energy inside of the system must be able to produce the enough energy to supply the bigger equipment if this bigger equipment fails. Okay, therefore we will have more systems ready to be inside of the system. The machines are rotating, but they are not producing energy, but they are consuming fuel. Therefore, only for this reason, we are increasing the prices of the grid. It has a very huge cost impact in the energy production. And also we have unused units only to be ready if anything happens. And also there is a retribution framework, and a large amount of technology cannot be put inside of the system because the companies are only allowed to use the refurbishment of several parts of the equipment, only the 5% of the equipment, and also only type of fuels. They cannot change to new fuels, electrical fuels, alternative fuels, and so on, because the companies will not receive money to produce energy with another thing. So in the case of the large-scale storage, this is a simulation of the Chira system is in our neighborhood island, Gran Canaria. So the first problem is, well, the time frame, okay? Because the deployment of this infrastructure will last between 15 and 20 years. So this is not a quick solution. Also, it has a huge public investment to do these things. And nowadays, in all Europe, there is not a retribution framework for the energy that is storage. We can think, for example, in the case of batteries, to accomplish the demand with the energy storage with lithium ion or lithium polymer or other kind of technology. Nowadays, it seems to be with a private investment, but the companies don't want to invest because there is not a retribution framework to use these things. Therefore, they are thinking how we can use this technology. From the technical point of view, it's very clear from all European directive, but not how to be used inside of the market and how is the retribution. No, this is not a barrier. And in the case of isolated system, the water scarcity is a very big problem. Our water is limited. In the case of the island or isolated system, that you have the enough orography, water wells, and so on, it could be enough to accomplish the water demand. But if not, we need to increase the dissolved water production using desalination processes. Therefore, it's necessary to include this new load inside of the planification because we are running out, our water reservoir that we have in our islands. And therefore, this is a very big problem because the desalination plants will consume an average between 2.5 to 4 kilowatts hour per cubic meter. To be honest, the new devices are reducing the power consumption, but as the time is going on, we need to include this load inside of the system. Also, when we are using renewable energy, we have several problems with two issues. One of these one is the voltage drop. If there is any contingency inside of the system and the voltage is going down, the system normally switching off. But when you have an isolated system, the system must react to do these things. And they need to inject a lot of current to keep the power inside of the system. And to manage these things, not all the renewable energy could be used to accomplish these things. And also, the other problem that we can have if we are making a transition inside of renewable energy is the synthetic inertia. The inertia normally is necessary when we have an equipment that is rotating, okay, in the conventional ones. In that case, if we have a small switch off of the system, the mass is still rotating and then can reconnect. They have approximately 2 seconds to reconnect all the system and nothing happens. But in the case of renewable energies, you have not anything that is rotating. You have power electronics. And therefore, it's necessary to create this synthetic inertia to make more resilient the system. A lot of researchers are working inside of these issues. Electrical mobility, well, in these days, it's not so clear if we need to make a transition to electrical vehicles or not, or if this is enough or not. But if we think that this is the way, we will face another new problem. This is a social forecasting of how the people is using the transport. We are not using the transport every day in the same way because we can move to another way. We can need to visit some familiar friends, or we need to go to supermarket. And to make this forecasting is quite complicated, but remember that you need to make a forecasting of the total demand inside of the system to do these things. We can introduce also the hydrogen. Hydrogen is not an energy by itself, it's an energy vector, like a primary energy in a fuel. So in that case, if we want to produce the H2 in our isolated system, we need to increase the renewable energy generation that we have to use this surplus of the energy to produce the H2. In that case, what is the most suitable option? To increase the accumulation with an efficient of 85% approximately, or to increase the renewable energy capacity to produce H2, taking into account that approximately the 10% can be used to capture using CO2 captured to obtain synthetic methane, or to use a car with a fuel cell for mobility. So the efficiency of this one when we are using as a final thing is quite interesting. One of the most social problem that we have is the possibility that we will have an external dependency of H2. So what does it mean? So our systems are moving from the importation of fuel, oil, diesel, and so on, fossil fuels, to H2, but we continue with an external dependency of the things. Well, we have a very good example how to make a transition to 100 renewable system. It's on the way, and they are learning a lot of lessons in Hawaii because they have been trying to reduce the demand of the electricity, increase the renewable energy inside of the grid, utility scale, and also home scale, and also to increase the grid flexibility. They are changing also the grid to avoid several of the problems that they have addressed. So the idea is to change the technology from the grid following system, the inverters, power inverters used in renewable energy that are copying the frequency, to grid forming technology. This technology is producing by itself the desired frequency, and they have a small range to move, but they can keep the frequency of the system. This is related with the synthetic inertia of the system. They are investing in storage using batteries, and also they are using the energy surplus, and the market condition to use the energy surplus is very clear. Therefore, the people is investing in this technology in home scale and also utility scale. So to finish, I want to ask to the audience two questions. So because I have not a real answer of both of them. So would it be possible to produce enough energy to the island to operate autonomously? I don't know. Perhaps it's necessary to import energy, to interconnect, or to see. Should we replace one energy source with another one. So we are thinking to move to H2, but are our isolated system ready to produce their own energy and their own H2? So thank you very much for your attention and your time.
Thank you, Benjamin, very much for this informative and very interesting session. Yeah, you ended up with a couple of questions to the audience. I don't know if you would like, is anybody interested in commenting or trying to answer any of Benjamin's questions for the end, or do you have any other comment? If you stop sharing, perhaps that we could see each other more as well.
Okay, let me see where I can stop sharing.
Yeah, great.
No, I cannot stop it.
Okay.
Okay.
Okay, great.
Okay.
Thank you. Okay. Any thoughts about Benjamin's questions in the end, or any comments? I could start up then, because I think that what you asked in the end is very interesting, and at least since this is not, I'm not an expertise in any way in the area. I think that the solution needs to be divergent and comprises of many different parts to just to change and have one solution would be very the security issue, and also the dependent on one single producer of would be very hazardous. That's at least my thinking on this. But I also have another question for you, Benjamin. I think that we all agree upon that the decarbonization is important, that we need to do this, and we could do it in many ways when it comes to transportation, buildings, and such. But at the same time, the demand of electricity is increasing. So that must be challenge as well, that we need both to decarbonize and at the same time increase the amount of energy in the systems.
Yes, indeed. I have an example about that. So a couple of years ago, when we were working together in a document, when I fill up my part, I sent to you by email. Okay, so you can take into account the time that I've been in my computer, that I've working with the energy that I'm using to this one. And I send you, for example, by email, so my internet connection, the server, and you have the information in your computer at the time that you are working in your computer. But now we are working online documents. So there are servers and backups around the world. So of course, we are increasing the quantity of the energy, not at the user level, also at the enterprise level and the all levels. So we are using social media. So there is not one computer, and a lot of computers around the world connected 24 hours, 7 days per week to give us these services. So we must be aware of how we are using this energy. And of course, energy and the social pattern are absolutely together. The energy is modifying our social pattern, how to use it, and our social life. And our social life is changed how we need to produce our energy. So this is not symbiotic, but they are together. So we need to be aware for this one. In that case, the energy transition is not from the technical point of view. It has a lot of parts, the social, the human behavior, and also the health and so on. They are all together to do these things. So we need to be aware about these things. So energy is modifying how we are facing our challenge in the world, and we are increasing or modifying our social life or our common life because we have the possibility to have energy over there. It's not easy in that case. So for this reason, it's necessary to have different point of view inside of the decarbonization. Both of them are quite important. Perhaps from the point of view of the technical devices, it's more or less clear how it's possible to do several things, but it's necessary to know how we can do that. So rules and implementation and so on, and also to be aware how we are using the energy and if this is really necessary to use, how we can use this energy and so on.
Yeah, so they're different. They're both behavioral, social parts, how people the demand and the technical part of actually producing, distributing, and how that affects each other. So they are symbiotic in that sense of how we actually demand the different things. So, yes, thank you very much, Professor González Diaz, for this interesting talk. I would just like to say that we will continue with the talks. There will be new ones advertised for the autumns with different topics. The dates and content are not set yet. The editorial board will meet in end of June, but it will be advertised through the different channels of the Stars EU Alliance when it comes to the Nova newsletter, the website, and in different ways. So thank you all for participating, and not least thank you, Benjamín González Diaz, for your very interesting talk on this important issue. So thank you all for today, and we'll see more and of each other in different ways and formats in the future. Thank you very much.
Thank you.